I saw many new buildings. People still call me as a condensed matter physicist. I am still doing some editorial work in a journal, condensed matter physics part. But I've been doing quantum information theory and quantum computation since year 2002. And today I will talk about some very recent and exciting developments in the field, and some of our work also. But I think you hear more and more about this principle or its related concepts in forthcoming years. Even if you are not a physicist, even if you are not an expert working in the field, you might recognize that these equations are equations from special relativity. There appears c, which is the speed of light, and v over c is the unit of quantity. They are indeed, they are not as famous as E equals mc squared, but they are actually what we call Lorentz transformations. Not Einstein, not special relativity equations, but Lorentz transformations. They were known before Einstein. And what Einstein did was, given some mathematical equations about the length contraction or time delay, a physical explanation. And in fact, special relativity is nothing but just two answers. Physics is the same for everybody, independent of the observer, in the sense that if you are moving constant velocity, you are not accelerating or opposite accelerating, you observe, you end up with the same laws. Similarly, the speed of light is the same thing. Unfortunately, we don't have the same thing for quantum mechanics, which is now 100 years old theory. What is quantum mechanics? It has many different aspects, but let me mention one very simple special group, what we call trace group. Quantum mechanics is, in some sense, linear algebra, that is some of our engineer friends tell from time to time, but it's a very special one. It involves permission operators. A matrix, another one. This one is called advanced matrix. It is a special permission operator in the sense that it has trace one. It will sum all diagonal elements, they add up to one, and all eigenvalues are non-neutral. So you multiply these two matrices, evaluate the trace again, at the sum diagonal terms, you find the mean values, expected values, expectation values. This is the physics of quantum, or mathematics of quantum mechanics. Why do we do so? Why do we have trace rule? We don't know. In fact, there is now a well-known phrase by David Byrne, Shadana Calvert. In fact, Byrne was very anxious about being the owner of this word, and from time to time people started to say that it was Feynman or even Dirac who said this, and just for this purpose he wrote an article on Physics Today. It was me who said this. If you have a proof for Feynman saying such a thing, please tell me. Well, that was the situation, and everything started with Bohr. I don't like giving similar talks or same talks. I'm showing the same picture, so I looked for something new, and I learned that Cambridge University opened the archive. They published some new documents. In addition to this lesson of picture of Bohr, a letter you might perhaps see Max Born for his ending his status in Göttingen University, that is by Adolf Hitler. After that, he moved to Cambridge, and he was the supervisor or teacher of, I think, 9 doctorates, including all forms of quantum mechanics. What we call Copenhagen interpretation or Born's base with Einstein all started more than 100 years ago. If you ask what is the difference between qubit, quantum bit, and classical bit, or classical two-state system and a quantum two-state system, people might tell you that in classical one, you have, say, one and probability for head and tail. In quantum one, you have superposition. Superposition, what is it? Well, it is something like this, yes, but what happens after that? You do a measurement, believe or not, you end up with, again, with one half probability, head, one half probability. let me tell you here, there is no difference between bit, classical bit, and quantum. As far as you do some measurements, you always get some probabilities, up and down, head and tail, the same result. There is no difference. In fact, you can mimic a quantum bit using classical random numbers. For instance, again, a well-known recipe, don't ask, I don't want to say shut up and calculate. An observable means a Hermitian operator for a bit, 2 by 2. And any Hermitian operator can be written as a linear combination of these, what is called Pauli matrices or XYZ matrices. You can easily check. You can find your own matrices, but any matrix, 2 by 2, Hermitian matrix can be written in this way. And it is easy to calculate mean values because if you have a 2-level system, spin up, down, neutron, photon, whatever, it is possible to parameterize this as a unit vector, or unit sphere. So you can calculate the mean values. So this is the quantum mechanics of a 2-state system. And you can regenerate, you can repeat it using a hidden variable model. An example, you can prepare your own method. Let n be a random vector, classical random vector. Then, given n, if you apply this rule, the value you obtain is a0 plus a or a0 minus a, depending on these conditions. If you do an averaging over m, you can reproduce quantum prediction. There is no way to distinguish the two. In fact, this is an analog of what we call Chinese room argument. Can we distinguish between a man, a thinking man, a Chinese, or a dictionary which translates Latin letters to Chinese ones and Chinese to letters. There is no one-to-one correspondence, but anyway, then is it possible to distinguish them? In this four-qubit case, one-qubit case, there is no way. But then, if we go higher dimensions, there are some interesting problems, starting with 3. Then you might ask, what are the postulates of quantum mechanics in analogy to special relativity? There is a trace rule. Can we put some physical principles which forces us to accept this trace rule? By the way, there are some alternative methods to formulate quantum mechanics. For instance, it is possible to rewrite everything in terms of pseudo-Hermitian operators, or some other alternatives. You can develop your own math to reproduce the same. But what is the physics behind it? Well, one of them is, for sure, no signaling or no disturbance principle, which says that. Think of, for instance, 2 observers, A and B. I do something here, and I obtain some result. A obtains some result. If I add them, this is what is called, evaluative margin of a probability distribution. You end up with PA. But this must be the same number if I repeat it with C. So, doing something here, measuring something here, shouldn't affect some other event somewhere else. Okay? This is very important. This is, if there is distance, this is called as non-signaling. Otherwise, it is a special case of what is called non-disturbance principle. However, this is not enough. Because if you use what is called non-signaling principle or non-disturbance principle, you can obtain some predictions beyond quantum mechanics. Quantum mechanics makes some predictions for some quantities. Non-signaling principle is beyond this, which means that we should add something. That is why there was a question mark in the previous slide. Example, Bell-type inequalities or contextuality inequalities. This is a version, simpler version of original work of John Bell. Let us think of variables again, A and B. A, B can be +1, -1. A prime, B prime can be +1, -1. Let us look at this quantity S. We have 2 possibilities. A and A prime are the same or different. If they are the same, the result is 2AB. If they are different, the result is 2AB prime. In any case, you see that S is either plus 2 or minus 2. So if there's a chance to repeat this experiment, and if A prime, B prime are random, average will be between the two. Your grade average is less than your highest and greater than your lowest points. So it must be between 2 and minus 2. But in quantum case, you find some examples where you can do this kind of measurements for those who had some experience with quantum mechanics. Let me give the name. For instance, you can take two spin-1 objects in singlet state, okay? Then, if you use for A projection along this vector, A prime a projection along this and this, so you can think of Stenger apparatus in Feynman's language, for instance, aligned in these 4 directions. If you evaluate this, you find that S can change between 2 square root 2 and minus 2 square root 2. It can go beyond 2, it can go below 2, below minus 2. Why is this so? Why do we have this violation? It means that we have something contradicting the previous argument. The contradiction is existence of a probability distribution for P, for A prime, B prime. But on the other hand, if you use non-signaling principle, the problem is unfortunately more difficult. I will come to this after showing. I keep mentioning John Bell. This is again one of the recent pictures. This is Bertelmann. This is John Bell's view when he was in CERN. When we talk about John Bell, we give as a reference this article, which is rarely available. The correct source is actually, this article is also inside this book. Everything is there, everything, and previous argument also started with this work. But the problem we are talking about was originated again 80 years ago by Einstein, Podolsky, and Rosen, because Einstein was first and his colleagues who recognized the problem of having A and B observers, distant observers, who are spatially separated, in the sense that the experiment takes, say, time t, multiply time t with speed of light, then put these A and B further than c times t. It means that during the experiment, there is no way for these observers to communicate. And no event here can affect any event here. All right. So this is why we put this no-signal principle there. If we put no-signal principle, I said it is not enough. Why? For instance, this plus this must be equal to this plus this, right? This plus this must be equal to this plus this. This is no-signal principle. If I put no-signal numbers inside an example, I can obtain this. This obeys no-signal principle. But if we evaluate the S, A, B prime, A prime, B minus A prime, B prime, you can easily see that this table or this box gives 4. It not only violates 2, but it also violates 2 square root. So it is too much. It means that no signaling is too generous. We should add something which restricts 4 all the way down to 2 square root. What is it? But I think a good starting point was the contribution, one of the greatest contributions in the field. It is my pleasure to have Professor Kleachko here, and in the group we had Alexander Shmansky and Mohammed Ali Can. Sinem Binicioglu is unfortunately not in this picture, but our colleagues discovered 10 years ago an equation, something in fact simpler than Bell or what we call CHSH inequality, which involves a single system which has nothing to do with entanglement. It is the simplest ever equation which shows, starting for these 3-dimensional systems, quantums, in the sense that in 2 slides you will see why it is not possible to mimic 3-level systems, a +1 or -1 form this expression, more symmetric than the previous one. You can easily see that this number cannot be less than -3, like antiferromagnetic equivalence matter systems, plus minus, then there is a frustration between 5 and 1, it can be -1, so you can see that it -2 will come. But as in the case of Bell, Clauser-Porn, Schmon-Holt inequality, the previous one, there is a way to violate this in quantum mechanics. If you take a spin 1 object, and if your spin is spin 0 along the z-axis, then there is a well-known fact for spin 1 system, you can measure spin square projection or projection square along perpendicular directions simultaneously. Again, for those of you who have some experience with quantum mechanics, this means that the two operators commute, so you can measure them. And putting your fingers, 5 fingers, making adjacent fingers at right angles, you can easily see that there is a star or pentagram where you can have a closed circle to realize this, and there is a violation. This is below -3. This is another example where we have contradiction or some incompatibility between existence of a joint probability distribution and a quantum mechanical. Here, the same thing. You might say that. Let us not call this as no signal, but no disturbance in this case. Okay? If I accept no disturbance, this time S should be violated, not by this number, but what? -5, right? This one will be -1, -1, -1, -1. So it should go all the way down -5, but it does not. What stops it? We're not talking about violations. We know that there is something beyond classical physics. There are no joint probability distributions. This was an old problem. This was the problem of 60s. This was the problem of John Bell. But now we are in year 2000. Our question is not the violation, but why don't we go further? Why does quantum mechanics stop at 2 points square root? Why does it stop at 5 - 4 square root? This is the question. And we want to derive this, of course, using not the trace rule, standard rule, using some Lie methods. Unfortunately, we lost Professor Shumovsky. I think a week later, you submitted the paper, as far as I know, right, to Theorem. And last year, we had a meeting in Bilkent University, what's called COVID-0, and I thank to Mohammed Ali Jan, the CEO of KCBS inequality, who shared this best known picture of Professor Shumovsky when he was in Moscow. I think it was a sort of tradition. Well, these are Bell inequality or KCBS inequality are examples of what is called coherent specular theorem. You can state the theorem in many ways. Simplest sense theorem is quantum mechanics contextual. In more technical terms, we can say that predictions of quantum mechanics cannot be reproduced or obtained by joint probability distributions. There are many proofs of the coherent specular theorem. This is called as the simplest one in the sense that you take, for instance, what you think of Kuchert system. You know that you can measure, do measurements, S-squared measurements along perpendicular directions, right? So I measure, say, along z direction, I obtain 1 over 0. And then I can measure in any direction perpendicular to this. And then, using some number of, certain number of vectors, directions, can you reproduce predictions using a joint probability distribution? You can find many configurations, contradictions. So this is how Cohen and Specker proved their theorem many years ago, 60s. And these inequalities are manifestations of this fact. So it was already known that for a Q-tip, for a 3-level system, you can't produce all the predictions using a joint distribution. But it was only year 2007, after our colleagues, to see some real, concrete example why this is so. There was no, but it was. Since then, inequality has been tested many times. You can see still many articles in Nature's or Discovery Letters testing KCBS inequality. One information, there is a trade-off between the two inequalities, KCBS for a cubic system and CHSH or band inequality between the two systems. It is possible to show that there is a monogamy if you violate the first one, if this goes below -3, this cannot be 2000 square root, right? So you can't violate the two. But I could also say that there's a room for polygamy in the sense that if you do a technical measurement for a qubit, it's possible to violate both. But this is a little technical, so I will just jump to some application of this side. As I said, it was very fascinating, and I am sure that forthcoming quantum mechanics books, perhaps there are also some examples, will include a discussion about KCBS inequality. Having such a very important contribution from our colleagues and two of my students, I was so excited, and I would like to spend 5 minutes or so about some aftershock of this development. Because soon after their paper, there appeared some papers or ideas saying that quantum computation or quantum computers run faster, or quantum speed up is there because quantum mechanics is contextual. And then, if a even single qubit is a contextual system, we can see for the Wien-Spiegel theorem or KCBS inequality, why don't we have a quantum algorithm showing speed up? There was no. And thanks to this third gauge, you can find such a simple example, which is actually the simplest ever quantum algorithm. So the idea is, given such distributions of 3 balls in 9 squares, no balls in the same row or in the same column, can we distinguish whether X squared is from the first row or second row? Or, given, again, one of these cards, how many questions or how many checks should we do to answer this question? In classical case, it is easy to see that between 2, because if you have, for instance, this left upper square is full, you can find an example in the second row that the same is true. So you need 2 computations. But in quantum case, you can do this with a simple one. With some simple math, you can see that these are just permutation operations, and we have 6 permutations, 3 of them are odd, 2 of them are even. First row is even, second row is odd. So then you can say that let me construct a machine where I have these permutations. There is no difference between this and classical trait, as in the case of bit and quantum. But for a quantum trait, you can do something else. You can prepare a superposition state here using Fourier transformation. And if you send this through this machine, I will run through this slide very fast. It's not our discussion. You can easily see that if you have an even permutation, the output of the first row is always the same. Psi 1, psi 1, psi 1. If you have an odd permutation, the output is the same. Psi 4, psi 4, psi 4. So with a single run, using this circuit, you can easily recognize, instead of classical 2 operations, for quantum case 1 operation, whether the permutation is even or odd. And this has been, this is claimed to be a new quantum algorithm class, and this has been tested many times since its first publication. This is an experiment with NMR circuit, another NMR, quantum photon experiment, and photon experiment. And this is the original article. If you are interested, you can have a look. It is as simple as I stated. So with some elementary quantum mechanics, you can follow the theory part at least. I can't say that I understand very much the experimental one part, but this article is an experimental article at the same time because I was about to quit the publication, but this group in Brazil proposed to join the two works. So this is the only official published version of the algorithm. And they used, they advertised the work so much that this is a web page from Brazil to be typed, I can say. And also it is now known very much in the literature, and there was even, I heard, a fifth experiment on this algorithm. And by the way, it is still not clear. I'm still now in touch with some colleagues in France about to understand the origin of the speedup. It's not clear whether it's contextuality, but for me it's clear that it was the motivation of the KCBS inequality to the world. Well, let us go back to no signal. I said that no signaling is not the only axiom. It is too relaxed condition. We should add something on this. But still, if you start with no signaling or no disturbance and use partly existing formalism of quantum mechanics, you can solve some problems otherwise unsolvable. One example is cloning. In quantum mechanics, cloning is forbidden for a very simple reason. Theory is linear. If A goes to A, B goes to B, A plus B does not go to A, B, but A plus B, right? So this is the proof. And there's a physical reason. If you have a machine which can do perfect cloning, you can easily send signals faster than light. That is instantaneous. But then approximate cloning is perhaps allowed. It is. They were known, but this is the only way, only method, still, since it's an application, that you can obtain, you can derive cloning machine in the sense that the parameters in your approximate cloning transformation. So no signal is still useful. So you can use this principle purpose for your own problems. Well, while I was thinking about these problems, as Orhan Pamuk said it is in the Hayat, I ended up with this time not a book but a movie. I will try to show it, otherwise perhaps I will exit. Ah, yes, it's working. No sound. I hope for the sound, but I think you at least read. I wish you heard Earth's spectre. This is the spectre of Earth's spectre, spectre theory. And this was Fröbel's house in Zurich. Fröbel's well-known by the physicists. And the film is by Edwin Cabello. Edwin Cabello is a Spanish theoretical physicist from Seville. I think he is one of the earliest, perhaps the first of the people who recognize the importance of the KCBS method. He has now more than 10 or tens of articles using the results of KCBS. In fact, what I will talk in my last 15 minutes or so will be the main works portrayed by Cabello's. So what is the exclusivity principle? No signaling, no disturbance is not enough. We should add something on that so that we can reproduce some predictions or hopefully all predictions of quantum mechanics. We didn't reach the second day yet, but we expect this whole strong exclusive events, and they are at the same time n-wise exclusive. What does it mean? Specker, with his very nice voice, was saying that if you have some physical quantities to be measured, say 3, you can measure these two, then you can measure all of them. Or if you have 5, this two measurable, then you can measure 5 of them. So this is the idea. This is not an easy statement. This is something beyond Kolmonov's axioms. What are they? You have a set of equal events. You assign numbers between 0 and 1, adding up to 1. That's all. But the E-principle is something different. But the E-principle, again, for those of you who had some exposure to quantum mechanics, it's very easy to prove. Quantum mechanics obeys the E-principle or exclusivity principle. Because if you have events excluding each other, say up and down, plus minus means exclusion, then if you don't, if you add all of them, if you count all the events, it is identity. If you are missing some of them, your projections are something less than identity. So if you evaluate the mean value, expectation value, of course you find something less than 1. Classically, it is very, very clear. Because if you have 2 exclusive events, then the probabilities are at most 1 or less. Let us now forget about trace-through, existing formulation of quantum mechanics, but just start from the very beginning. Quantum mechanics is a theory where we have probabilities. These are called generalized probabilistic theories. It obeys no disturbance principle. It might be very clear or simple for some of you, but it is fundamental. That is, if I have P, A, B, if I add over B events, I obtain probability for A. We accept this. Then we add this condition. Exclusivity principle. This is an example. Look at the first line. If you take, for instance, A1 plus A2 plus and A2 minus A3 minus, they exclude each other. Why? Because A2 is plus in the first one, but minus in the second one. Right? So if this happened, you can't have the second one. If the second one happened, sure, we can have the first one. Look at the second and third, this time A3 plus minus. Look at the first one and the last one, we have A1 plus minus. So these are pairwise exclusive events. And the principle says that if I add 3 of them, this can't be more than 1. This is something stronger than Kolmonov's axioms. Why? Because if you look at, in terms of standard probability theory, we can only say that this plus this is less than 1 because we have plus and minus. Or if I take these two, A3 plus minus less than 1, look at this one, minus plus less than 1. So I can add them. I find 2s less than 3, so s is less than 3 over 2. So it predicts, or the constraint by standard argument is something larger or bigger than the prediction of the E-principle. And if we return to KCDS, and if you use exclusivity principle, is it possible to predict the number square root 5? This is our question. Now, look at this expression. This is another way of writing the KCDS inequality. It is equivalent. There are many equivalent forms. It is already discussed in the original article, and thanks to Professor Kulayashko, who gave me an extended version as well. There are longer discussions. Look at this minus sign. Putting this minus sign there, you can write this as a number, this time larger, smaller than 3. So going beyond 3 is a violation. Okay? You can rewrite this expression S as a sum of two terms, the first line, and another line which I didn't write. It is obtained from the first one, prime is obtained from the unprimed one. If you make plus signs minus, minus signs plus. You can rewrite KCBS inequality as CKCBS is less than 2, but quantum mechanics says that it is violated till square root 5. Our aim is to show why does it go beyond this? Why is it square root 5? Now, let us do a KCBS experiment. Two experiments. One here in Bilkent, one in Sabancı. This argument due to Cabello is very, very interesting because for me it resembles the argument in Einstein's book on special relativity. You know, he has taught experiments, and at every point he uses the constancy of speed of light. If C is same for everybody, then you derive the Lorentz transformations, the equals, square, etc. Now, here we are assuming that KCBS is a universal inequality. Here, whether you do your experiment in Ankara or in Istanbul, you will obtain the same number. Let us look for this. So we have two pentagrams, two experiments, and let us denote the numbers to be obtained in Bilkent as B, and here is A. Okay. Of course, these are independent events. Two different laboratories or two different theoreticians doing the calculation. And we can write the joint probability and figure out because they commute in technical terms as a product. So in this way, you can form many exclusive events. Here we have 5 lines. You can easily check that these are all exclusive. For instance, let me take the uppermost and the lowermost one. 5, I don't have that. Oh, A1 minus A1 is plus that. They are exclusive. Or if we take, for instance, these two, 4, 5, B, can you find something exclusive here? A5 minus A5 plus. You can check that. Pairwise, they are all exclusive. Then E principle says this number is the sum of them, less than 1. In fact, you can draw such a diagram, and you can draw 4 more such diagrams. Again, 4 more such inequalities, and you can add them. So you add 5 lines, one by one. These are the diagram that you have already seen. These are the other 4 diagrams. And you can easily see that, let me go back, the expression that you obtain after summing all these 5 lines, I don't want to show you too many equations, is exactly the equation you obtain where you multiply 2 KCBS expressions. KCBS written for A's, KCBS written for B's. You multiply them. Okay? So it is square of it. It is less than 5, so it means that KCBS is less than square root 5. So this is how to produce or reproduce prediction of quantum mechanics using exclusive principle. Again, let me repeat, if you do the same calculation just with no sigmoid principle or no disturbance principle, we would expect a violation of the standard form of KCBS inequality all the way down to -5. But the E principle or exclusivity principle, or sometimes it's called as global orthogonality principle, stops this. Okay? Yes, this is all that I would say. I want to finish and leave some time for the questions if you have any after 2 lines. First of all, this was a discussion about KCBS. But you can derive 2 square root 2 of CHSH as well using the same expression or principle. And now it is time for us or for you to look for possible other predictions of quantum mechanics, reproduce them using E principle. Or perhaps you can be more ambitious and you may want to derive the existing formalism traced through starting from E principle. Is it a mathematical consequence? At least for these 2 very fundamental expressions, which were not derived previously in other methods, we have at least a positive answer. This is a dream, that's why I wrote it in.